Hey everyone, so today I'm just going to talk to you briefly about Newton's Law of Gravitation. So, Newton's Law of Gravitation deals with any two objects in the universe. So, any two objects, as long as they have mass, are going to be attracted to each other by a force we call gravity. Newton's Law of Gravitation describes the size of the force between the two objects, and it's influenced by two things. So, if we look at the actual definition for Newton's Law of Gravitation, we'll see what those two things are. So the definition states Newton's law of gravitation says the force of attraction between any 2 point masses, so they're just things that have mass, is first of all directly proportional to the product of the masses, and secondly, it's inversely proportional to the square of the distance between them. So if we break down what each of those two things mean, if the force is proportional to the product of the two masses, that means that the bigger the mass of the two objects are, the greater the force of gravity between them. So this means that if you're standing on one side of the room and a friend, for example, is standing on the other side of the room, there would be a force of gravity between you, but because both of your masses are quite small, the force of gravity attracting the two of you will also be quite small. If we look at an opposite example, if we have something like, for example, the sun and the earth, because both of those bodies have a huge amount of mass, the product of their masses will be very big if we multiply them. So therefore the force of gravity attracting the sun and the earth to each other will be quite big too. It's important to note that like any force, it's going to work both ways. So this is a force that the sun is exerting on the earth, but also that the earth is exerting on the sun. So they're each pulling them towards each other. Second part of Newton's law of gravitation says that the size of the force of gravity is inversely proportional to the square of the distance between them. So we could say, if we want to put that in symbols, that force is proportional to 1 over the distance squared, or inversely proportional to the distance squared. This means that as the distance squared gets bigger, the force gets smaller, or if the distance squared gets smaller, the force gets bigger. Intuitively, this kind of makes sense as well, because we know that if we were very, very close, for example, to the Earth, like we are now, the force of gravity attracting us to the Earth is big enough to hold us there. But if we were to travel up into space, then the force of gravity acting on us will be much smaller because the distance has increased. So bigger distance, smaller force of gravity. Smaller distance, bigger force of gravity. Now there is a formula accompanying this. You do not need to know the formula off because it's in your log tables. But it's basically a combination of the previous 2 points. So here we have the force caused by gravity, and it's equal to big G, which is the universal gravitational constant, times the product of the two masses, so the mass of the first object, the mass of the second object, divided by the distance between the two objects squared. Now, the first thing we have here, big G, or the universal gravitational constant, is not a value you need to know. It is in your log tables on page 46 or 47. Its value is 6.7 by 10 to the power of minus 11. It should say 10 to the power of minus 11. Newton meter squared per kilogram squared. You don't need to worry too much about the unit, but you do need to know that it's 6.7 by 10 to the power of minus 11. Everything else here is fairly self-explanatory. We have M1 and M2, like we said, that's the masses of the two different objects. And we have D, which is the distance between the two objects. Now it is specifically mentioned on the syllabus that you should be familiar with the idea of an inverse square law. Exam questions on inverse square laws don't really come up very often, but if they do, it's usually asking for you to give an example of an inverse square law. So you could just use Newton's law of gravitation as your example of that. The fact that it is an inverse square law, because our force is inversely proportional to the square of the distance. So inverse because it's inversely proportional, and then square because it's inversely proportional to a square. What this would look like if we graphed the relationship between force and distance, we would see that when distance is small, the force is really, really big, but as the distance increases, it drops off quite quickly. So I'd also be familiar with this shape of the graph in general, but again, exam questions haven't ever really been asked on the specific shape of the graph. It might just be something that helps your own understanding, but it's not necessary to learn off. So before I finish the video, I just want to talk to you about one place that I often see questions, both textbook questions and exam questions, trying to trip up students. So it's a really common little trick they use, so I think it would be reasonable for you guys to be expected to know it. So looking at the formula here, if you're asked to calculate the force between two objects, it could be two planets or it could be a person on a planet. The mass of both objects is going to be pretty constant, so they can't really trick you too much there. Same thing with the universal gravitational constant, or big G. It's just 6.7 by 10 to the power of minus 11. It never really changes. So where they do try and trick you is with the distance, d squared here. So for example, they might give you an astronaut. They might give you his mass, so we can say mass 1 or her mass. And they might give you the mass of the Earth. And they might ask you to calculate the force of gravity that's attracting the astronaut to the Earth. So you'd put in your universal gravitational constant, might put in your mass for the astronaut, the mass for the Earth, and they may give you the distance between the astronaut and the Earth. So they might give you this distance here. And a lot of people, fairly understandably, would put this distance in as the distance between the two bodies. But that is actually not the correct way of doing it. The trick is you want to get the distance between the centers of the two bodies. So you want to find out the radius of the planet. It's probably given to you somewhere in the question, but they're just trying to be sneaky by breaking it up into the radius. Then you'd add on the distance. This will give you your actual distance then to fill into the formula, which is the distance between the center of the astronaut and the center of the Earth. So that's just something to keep an eye out for. It's probably a trick you're going to see quite often.